Thank you so much. Thanks for the introduction, and thanks to the organizers for inviting me to join. I've never been to this conference before, and I'm really excited to be here and get to meet you all and hear the other talks. So today and tomorrow, I'm going to be giving a tutorial on a field called conformal prediction. So just to lay out sort of the plan, today is going to be quite introductory. So if you're familiar with conformal prediction, please feel free to take a nap / go do something else. Today is going to be the beginner version from sort of a more theoretical perspective. Tomorrow I'm going to be talking about some more recent extensions in different settings that will perhaps be new even to many of you who are familiar with the basics of the field. Okay. So by the way, please feel free to stop me with questions throughout, and we can get however far we get today and make it up tomorrow. Okay, so let me start by laying out the setting. So conformal prediction is, at least in its most basic version, a methodology for supervised learning settings or regression problems. So we're talking about XY data where we have features X and we're trying to predict a response Y. I want to say from the beginning that for sort of intuition, I'm going to primarily be talking about the setting where Y is continuous. So you're actually trying to predict a real value. But a lot of the principles here also apply to settings where Y could be something else. It could be a categorical label, it could be a high-dimensional object, but we will mostly talk about regression where Y just lives in the real line. So in statistics, speaking very broadly, we often want to learn about the nature of the relationship between Y and X. But in order to be able to do so, generally it is absolutely necessary to make some kind of assumptions. It doesn't necessarily have to be as strong as I believe the linear Gaussian model is true, but at least something that says learning is possible. For example, smoothness conditions in a non-parametric setting. But if we only want to do prediction, I'm not trying to make claims about the nature of the relationship between X and Y. I just want to build an accurate predictor for Y given X. Then we can be more flexible because, of course, it is possible to do prediction in real life. And in real life, most assumptions do not hold, or at least do not hold exactly. So for predictive inference, we want to predict the value of Y given X. So we have n training points, and then I have some future test data for which I want to predict. But the term inference here means that I also want to be able to state something about the uncertainty around my predictions. So not only do I predict the value of Y, but I also would like to make some kind of confidence statements about my prediction for the value of Y. Okay, so let me take a minute to just kind of orient conformal prediction in the space of statistical approaches, again, speaking at a very loose level. So traditionally, we might take a classical approach where we assume a parametric model, and then when we ask questions about our data, we ask them by phrasing questions about the parameters. So we would perform estimation of the parameters and inference or uncertainty quantification about the parameters. And then if our goal is actually prediction rather than learning about the parameters themselves, we could use the parametric model that we fitted to provide prediction intervals. So what this might look like is a Gaussian linear model. We then have closed form expressions for the distribution of our noisy estimates of beta and sigma squared. And then we can have just an equation for the prediction intervals that result from those estimates. Moving to slightly more recent things, if we don't want to believe a parametric model, we might move to non-parametrics. But again, sticking with a bit more of a classical approach where we make enough assumptions that we can still make strong claims. So for example, we might assume some kind of smoothness in the underlying relationship between X and Y. We might use something like Gaussian kernels or nearest neighbors or some other method that relies on those smoothness assumptions in order to be able to say that our estimate of that regression function is at some rate that we know, converging to the truth, and then again provide prediction intervals. Now, if these things are either not reliable assumptions, or maybe we want to be a bit more state-of-the-art and use something that's not a kernel method, but a more modern method, we could take a more machine learning style approach. So we might train an over-parameterized model for Y given X that's much more flexible than something that assumes strong smoothness conditions. And we provide predictions for given new X's for the unobserved Y's. But then what do we actually do to provide a prediction interval that when I predict the value of y, like this patient's outcome will be blank, what's my margin of error? Or when I try to classify, like this image is probably a cat, what's my uncertainty? Like, is it maybe a lion? And so in this type of setting where we're not in a assumption-based, model-based approach, it's tougher to know how to make uncertainty quantification statements about your predictions, even though the predictions themselves are often more accurate, more powerful, and make better use of the enormous data that we might have access to. So a common approach is to use data-driven strategies. For example, to use holdout data to say, well, typically on my held out data set, errors tend to be within a certain range. Let me use that to figure out how much uncertainty I have about my predictions. But what is a statistically principled way to do that? And so the question that conformal prediction aims to answer is that when we're using methods that either are not even necessarily based on an explicit model, or maybe they are, but we don't trust that the model is necessarily true, how do we use the data itself to provide uncertainty quantification, to provide some notion of prediction interval or confidence interval around the predictions that our models are making? Okay. So why is this a challenging problem? And it's because the approaches that I've outlined so far, which is kind of, you know, my like 10-second history of statistical approaches to this problem, they all have certain drawbacks. So parametric models could just be wrong. Non-parametric models that are valid under certain conditions, those conditions could be incorrect. And for a more flexible approach, like an over-parameterized approach that can fit a richer class of models, we don't have explicit formulas like you do for linear regression for how to build that prediction interval. So this is kind of the space that conformal prediction is starting from, is how to resolve these things. Yes?
Are we going to always assume the data is IID, like the train and test data?
Great question. So for today, yes. Or actually exchangeable rather than IID, so that's a relaxation, but still you don't have distribution changing over time. Tomorrow I'll talk about extensions in that direction. Okay, so what are our choices when we're sort of faced with these options? We could rely on the assumptions being correct, so cross our fingers and hope for the best. We could try to empirically test whether the assumptions are true, so some kind of goodness of fit testing. And the challenge with that, like that sounds great, right? Just check that your assumptions hold and then use those assumptions. The challenge with that is that constructing a test that will reliably detect that assumptions fail is generally impossible unless you make some other assumption. So we kind of can't break out of the vicious cycle where in order to be able to do something that relies on assumptions, we need to make untestable assumptions. So finally, we can try to create inference methods that don't rely on assumptions or perhaps rely on like the weakest possible assumptions. And conformal prediction is sitting in that space. Okay. So what can we do if we want to do some kind of data-driven predictive inference? So just kind of building our way up to the conformal methodology. So again, we have features and a response. We have training data, and let's use it to fit a model. So this mu hat is some model that's predicting y as a function of x. And then I have future test points, future x's, for which I want to predict their corresponding y's. So just to be completely clear by what we mean by prediction versus predictive inference, prediction asks you to predict the value of y, whereas predictive inference asks you to quantify your uncertainty around your prediction. And so I want to distinguish between these two because a lot of machine learning strategies are constructed and designed to answer the first one, but not necessarily the second one. So conformal prediction is not trying to change how we do the first one. It's trying to say, if you already have a method that does the first one, how do we bring ourselves to an answer to the second question as well? So conformal prediction is not a prediction method. It is a procedure that you can combine with the prediction method that you already know and love in order to also provide predictive inference for your prediction method. Okay. So how can we do this? So let's start with an approach that does not work. And again, I'm going to be talking for intuition about the setting where I'm predicting a real valued y, but these principles transfer over more generally. So in practice, we would expect generally that models we use today are often going to overfit to training data, meaning that they're closer to training points. The errors that they make on training points could be 0 or could be extremely small, but that doesn't necessarily mean that I'm going to have 0 error on my test data. And so if the goal of predictive inference is basically to try to say how large will this be, the test error, answering that question by checking how large the errors were on the training data is not a reliable plan. And I want to point out that this is not a problem of non-IID data. This is true even for IID data because this is a problem that arises from overfitting. Now, of course, if the data is not IID, then we have bigger problems. But for today, we'll talk about we're sort of focusing on the overfitting issue, not on the IID issue. Okay, so just a 10-second simulation to make this a little bit more precise. Let's say that I'm trying to build, for example, a 90% prediction interval. So my coverage level that I'm aiming for is 1 minus alpha, where alpha is 0.1. So what I'm going to do is I'm going to take my residuals on the training data, and I'm going to take their 90th percentile, and I will use that to build this green margin of error around my fitted predictive model in order to try to get the right level of coverage. So on the training data itself, by definition, this has 90% coverage. Yes? Great question. So for now, we've actually not even laid out a framework, but they're about to be random. So the x, y pairs themselves are IID from a joint distribution.
Takes the residuals across the board to mix residuals on the whole x-axis. I mean, you might have very tight residuals at, for instance, here 2, and very wide ones at -1, but you...
Absolutely. So here, we're not even trying to solve that problem. We're only trying to solve the average over a random x problem, which is strictly easier. But of course, the problem you're pointing out, that you might need it to be wider in some x regions and narrower in other x regions, that's important as well, and we'll come back to that. But here, like, we haven't even solved the more basic problem of on average over x. Okay, so when we do this, on the test set, we're going to, by definition, have lower coverage because of the overfitting issue. And in particular, you can see in this picture that the fitted model is like a little too wiggly. We've kind of not smoothed enough. But of course, in practice in high dimensions, that's like a very challenging tuning problem to try to know how to avoid overfitting. Is that even good, or do we want over-parameterized models, as is often the case in machine learning methods? So this is not really a practical approach. Okay, so the standard thing to do in statistics and machine learning for a long time now is to say, okay, well, I know I shouldn't look at the training data to answer how good is my model, because obviously my model is good on the training data. Let me use a holdout set. In conformal, this is often called calibration, or the calibration set. So I'm going to fit the model using one portion of my data, let's say half, and then I'm going to assess its error by computing the residuals on the second half. And the prediction interval is going to use the fitted model produced from the first half, but then the width of the prediction interval is going to come from the residuals on the second half. So the important thing here is we've separated these two tasks. The prediction problem is handled by the first half of the data, called the pre-training set, and the margin of error, the predictive inference question, is answered by looking at the other half of the data, which is separate, the calibration data.
Mm-hmm. So in your figure, actually, you should have the same width for your band, right?
It is the same width. It's because the slope is so steep, it's kind of an optical illusion. But if you actually look at how tall this is, it's very tall. It's just so steep that it looks different. Yeah, I know. It's just sort of a visual trick, an unintentional visual trick. Okay, so here's what this looks like, which is that once we have a separate calibration set, now we actually do get the 90% coverage we were asking for on the test set. Okay, so we might stop here and ask, did we just answer the entire question, right? Like, okay, just use fresh data, are we done? But of course, this is a really simplistic approach, and we could probably improve on it in so many ways. So first of all, as pointed out, perhaps we need different widths of intervals at different x's. Do we actually have to lose half our sample size when we do model training? All sorts of different questions as to how we could make these ideas stronger. We also haven't answered this question theoretically. Like, do we need some kind of concentration of the residuals on the calibration set to like the right distribution to get coverage? What if my sample size for calibration is only 20? So we have lots of different questions to answer to turn this into sort of a fully fleshed out framework. But the general idea basically is we're going to find ways to use the data to provide predictive inference for a predictor that you already have and already want to use. Okay. So for using this holdout method, one thing that I mentioned just now is that if we reduce our sample size so that we keep a separate holdout set that wasn't used for training, we are gaining the ability to know how wide to make that margin of error, but we're actually losing accuracy in the model itself. And a natural approach would be to ask, okay, can I just use cross-validation to try to more accurately like pull all the information I have out of the data? That actually turns out to be much more complicated theoretically than we might expect. And I will come back to this, but towards the end of today. Okay. So now let's make things a little bit more formal about what we want to do in distribution-free inference. So in general, the term distribution-free inference means what it says. I want to answer inference questions without specifying a distribution or without specifying assumptions on the data distribution. But speaking specifically about predictive inference, we would like to be able to construct prediction intervals, or more generally prediction regions if you live in categorical or high dimensional Y. So some kind of subset of Y space, so that the probability of the Y being contained in that region is at least the 90% or whatever level that we want. I'm going to keep calling it a prediction interval, but it doesn't have to be an interval. We might not even be living in the real line. Now again, this is kind of a simple and weak goal. It might be that this holds on average, but it's sort of very different at different X regions. We will come back to those issues. For right now, let's just say that this is what we want to do. So why is this question not really well specified yet? Well, first of all, one solution is to return the prediction interval -∞ to +∞. Technically speaking, that does answer this question. But obviously, that's not informative. And so what we actually want is we want something that is valuable, informative, accurate, that still satisfies this. And furthermore, if we are only able to do this for methods that are really easy to study in theory, like nearest neighbors or something like that, that's great, but it means that we're sort of forcing ourselves to choose between the power of state-of-the-art methods for prediction versus being able to do uncertainty quantification. The real goal is to be able to start with any predictive method you want, so sort of whatever neural net architecture got invented yesterday and there's no theory for it yet, and to still be able to provide uncertainty quantification so that goals like this are satisfied without assumptions on the data. So in other words, we actually want to be flexible both about working for any distribution and working with any algorithm. Okay. So with all this in place in terms of our motivation and our goals, let me now move on to some of the theoretical ideas behind conformal prediction. So before I talk about conformal prediction, let me give a quick introduction to the idea of exchangeability, which is sort of the data framework that it's working in. So, in these tutorials, I'm going to use Z to denote the XY pairs to save space on the slides. So that'll be sort of fluid throughout. So far we've been talking about the IID data setting, where I can learn something on the training data and then deploy it on the test data. In particular, if I want to use the residuals on my calibration set to know how big my errors will be on the test data, we need something like an IID assumption. And again, I will come back tomorrow to the question of what happens if my distribution changes or becomes more challenging over time. But so far, we've talked about the IID data setting. So there, of course, are different opinions as to whether you can really call this distribution-free. Because if I think of the joint distribution of all my data, if I think of my data as a time series, for instance, an IID time series is a very specific type of time series. And so that really is a strong distributional assumption. The term distribution-free is referring to the individual data point distribution P, meaning that if I'm using if I'm looking at my XY pairs as IID draws from a distribution, that distribution doesn't need to satisfy a parametric model or smoothness conditions and so on. So I do want to point out that this terminology is sort of removing assumptions in certain ways, but not in other ways. And again, we will return to these settings tomorrow. Okay, so a relaxation of the IID setting that turns out to work basically the same way is what's called exchangeability. So just in case you might not be familiar with it, the definition of exchangeability means that if you take any permutation, the distribution of the data stays the same. A little bit more formally, we're actually talking about permutations of finite subsequences of the data. And of course, the IID data setting is a special case. Now, why is exchangeability basically the same as IID when it comes to the question of predictive inference? It's because intuitively, when we use a holdout method, we're saying that looking at holdout residuals is representative of what I expect to see on test residuals. So in other words, holdout and test residuals are essentially interchangeable. And that's exactly what exchangeability is saying. So IID is a special case of exchangeability. Conditionally IID, like I sample a parameter for my linear model, and then I sample IID from that linear model, a Bayesian type framework perhaps. That's another special case of exchangeability. If you're familiar with Definetti's theorem tells us that in an infinite sequence, conditionally IID is the same as exchangeability. Anything exchangeable is conditionally IID. In the finite case, I do want to mention that that's no longer the case. For example, in a finite sequence, if I don't have infinitely many test points, you could sample without replacement from a finite population. So that's another example of exchangeability. We're not going to worry about those distinctions here. I just want to point out that when I talk about training data and then test data, I'm not really making a distinction between whether I have one test point, a finite number of test points, infinitely many test points. All we're requiring is that each test point is that the holdout set is representative of each test point. So exchangeability within your sequence of data, whether it's short or long. Okay, so with all that in place, let's talk now about conformal prediction. So let me give a very quick sort of 10-second version of the historical background. And I apologize because, of course, this is a very rich field and I'm missing so many important references. But just in the interest of time, I'm going to talk about this very quickly. So the conformal prediction framework is basically the idea that we can do statistical inference, or more specifically predictive inference, relying on exchangeability of the data rather than any type of modeling assumptions / restrictions on the types of algorithms that you want to use. So this dates back, as far as I'm aware, to the late 90s, this 1998 paper by Gammerman, Wolf, and Vapnik. There's a really foundational textbook in 2005 by Wolf, Gammerman, and Schaper called Algorithmic Learning in a Random World. That's kind of the now classical reference for conformal prediction. For myself and for many statisticians in the US, our introduction to this field came from work out of the Carnegie Mellon statistics group, Jing Lei et al. This paper called Distribution-Free Predictive Inference for Regression, which brought a lot of sort of applied statistical questions through the conformal prediction framework, and has really been influential in this field as well. So these are kind of this is kind of the historical picture for me as to how I got introduced to this field. And again, this 2005 textbook is kind of like the definitive reference for the foundations of this field. More recently, over the past 5 or so years, it's become extremely popular in both statistics and machine learning. There are a lot of software packages, like large-scale software packages that have developed, including Amazon AWS has a package that incorporates conformal prediction. If you're interested in conformal from a more applied point of view, I really recommend this textbook, Conformal Prediction, A Gentle Introduction, by Anastasios Angelopoulos and Stephen Bates, published in Foundations and Trends. I just want to give you a heads up that there is a free archive version of that as well, but it's titled A Gentle Introduction to Conformal Prediction. If you search it that way, you'll find the archive version. Finally, Anastasios and Stephen and I are currently working on a theory book for conformal, Theoretical Foundations of Conformal Prediction. We haven't finished it, but the part we have finished is available on archive. The full thing will also eventually be available on archive. So here are just some references if you want a little bit more information about the field. Conformal started from these sort of foundational principles and these beautiful mathematical ideas around exchangeability, but of course it's answering a very practical question: how do I do prediction that's valid in a robust way? And so as such, it's been used in a lot of applications, particularly more recently as different versions of the methodology have been developed. So here's just sort of a very tiny sample of the different applications for specific domains in the sciences and in technology where it's been used. Again, it's really growing in popularity, and I think it's a field where statisticians can have a lot of impact. Okay, so with that extremely short background, let's dive into the methodology itself. So I'm going to talk first about a version of the methodology called split conformal prediction, which is basically a formalization of the holdout method that we just talked about. Okay. So formally, here's what split conformal prediction looks like with all of our sort of, all of the technical details in place. So first I have my data, and I'm going to split it into a pre-training portion and a calibration portion, half and half, for instance, or whatever fraction you like. And we're going to construct a fitted model using any regression algorithm. So I specify that because you don't have to use something that is a specific model. This could be, say, some iterative procedure that doesn't have like a closed form solution. It doesn't matter. Once we have a fitted model, we then compute our residuals on the holdout set, and we take the 90th percentile of those residuals, or whatever coverage level you want. But I do want to point out that there's this tiny correction factor here, where instead of taking the 90th percentile, you take like a tiny bit higher than 90, where n1 is the size of your calibration set. This is basically a correction for the fact that I'm using finitely many draws from the residual distribution, i.e. my holdout set size, and I'm trying to compute the quantile of that population. How big will the residual be on test data? Why the correction is exactly +1 over n1, we'll see in a minute. And then our prediction interval is of this form. Now again, this is just one specific version of the methodology. In particular here, the prediction interval has the same plus or minus width for any value of x. We'll come back to that question in a moment. Okay. So the fundamental result of conformal prediction is a procedure of this type has predictive coverage under IID or even exchangeable data with no further assumptions. So in particular, I want to point out that there is no assumption that the model that was fitted was good in any way. That model could be good or bad. And the reason that it doesn't affect coverage is because we use the calibration set to tell us whether the model was good and can get by with a narrow predictive interval, or whether I use totally the wrong model for the data and I need a very wide predictive interval. So here is the coverage guarantee. So let's see why this holds. So first, let me just streamline the notation. We're going to use SI to denote the absolute value of the residual for my holdout set and my test point. So in this case, we in practice often have many test points that we want to predict for, but I'm just saying n+1 is the test point since I just want coverage for each individual test point. Okay, so by definition of the prediction interval, the way that we constructed this C of x, the event that I have coverage is exactly the same as the event that when I look at the residual for the test point, it's less than or equal to this corrected 90th percentile of the residuals on the holdout points. Okay, now there's some tricks that basically deterministically look at the calculation and definition of a quantile, which says that these two inequalities are equivalent. And again, this is a deterministic statement, which is that if the quantity on the left-hand side, if I'd like to add it to the list of the things that I'm taking the percentile of, the difference between these two statements, like it's in the list versus it's not in the list, that difference is exactly quantified by taking the actual 90th percentile versus taking this corrected slightly higher than 90th percentile. So this is the reason for that correction factor. It's so that the interval that I actually calculate is equivalent to this event where the test residual is inside of the list. Okay, now why is that important? So now we have to look at how exchangeability is playing a role in these calculations. And it's because if I assume the data points are exchangeable, then the residuals that I calculate for any data points which were not used in training, those residuals are exchangeable with each other. Basically, we can think of it like this. first I train my model, and now let's treat it as fixed. From this point on, all future test points that lead to a residual, those are all IID draws from the same distribution. The distribution of what is the residual when I evaluate this model on data points drawn from P. Okay, so since this is true, the probability that this particular residual is in the bottom 90% of all the residuals is at least 90%. This is basically just saying that if I take an exchangeable list and then I look at one entry of that list, it has a 50% chance of being below the median, for instance. So this is just true by exchangeability. When you have an exchangeable vector, the ranks in which those entries are ordered is just uniformly random. Okay, so these are the basic ingredients, and we can see why exchangeability comes up, why it doesn't matter whether the model was good or bad, because regardless of the model, the exchangeability in this top of this slide still has to hold. And we can also see where that correction of the 90th percentile comes in. It's because in order for this statement to hold, I need to include the test points residual in the list that I'm looking at, and just then use the fact that when you have an exchangeable vector, the ranking of the entries in that vector are uniformly random. Okay, so this is split conformal prediction, at least in its most basic form, where we're looking at prediction sets constructed in this particular way. My prediction, plus or minus, I pick some constant for my margin of error. Okay, now coming back to that question of is that the right shape of the prediction interval? So due to the construction, there's no way that I could ever get different widths for different values of x. But this is not a failure of conformal prediction. It's just that we are currently looking at one specific implementation of conformal prediction for which by construction that's true. So why has our implementation led to this? Well, of course, it's just because this is the format of the interval that we've just defined. And an equivalent way of looking at this is that when I ask whether a value of y should be included or not included in my prediction interval, I am using its distance from the prediction as the metric to determine inclusion or exclusion, regardless of the value of x. So in conformal prediction, this is called the score. That quantity is the score for the value little y to decide whether it goes into the pink region or not into the pink region. So if we want the prediction interval to have a different shape and different qualitative properties, we just need to choose a different score. I'll come back to this a little bit later, but let me just give you a little bit of detail on how it looks to choose a different score. So the generic algorithm for split conformal prediction, again, we're still using data splitting to have this holdout / calibration set, is that on the first half of my data, instead of training a predictive model and then using the score, which is just the residual for that model, I'm going to more generally train any score function. So a score function is a function that takes in an xy value and returns the score, for example, the residual, with high values indicating you might not want to put this in the prediction region, low values indicating, yes, this should definitely go in the prediction region. Now, at the second step, instead of taking the residuals on the holdout set, I just compute the score using my fitted function. Sorry, apologies for this microphone. Okay, I'll try not to touch it. And then the prediction interval, although of course it's not necessarily an interval, it could be any shape now that the score function is arbitrary, is just all y values whose score lies in the bottom 90th percentile of the scores that you observed on the holdout set. So the version that we saw a few minutes ago, split conformal prediction specifically using the residuals, that's just defining the score function as the absolute residual relative to a particular fitted model. And with that score function, the construction at the bottom of this slide here can just be simplified to my prediction plus or minus, I tuned a constant margin of error. Another example is the scaled residual score, where if you believe or sort of see that your y values seem to have different variance at different values of x, we might want to have a prediction interval whose width changes with x, So the way that we would construct that is we would have a score function that looks at sort of a local notion of variability, like for example, an estimator of the local standard deviation. And again, the score function has to be pre-trained. It has to already be fixed before I look at my holdout data, meaning that both mu hat and sigma hat are trained on the first half of the data, and then these scaled scores are computed on the holdout set, the calibration set, and used for constructing the prediction interval. For example, here's this figure I grabbed from the Lay et al. Paper. We can see, of course, it's looking a lot better on the right-hand side than on the left. Now, I do want to point out that, again, conformal prediction works in our definition of what it means to be valid, regardless of whether the model/score fits well or badly to the data. So remember, the guarantee for conformal prediction is that when I look at my test points, I should have a 90% probability of coverage. If you look at this picture on the left, we do have a 90% probability of coverage. It's just very uneven. It's more like 100% on the left and much lower than 90% on the right. But technically speaking, the guarantee still holds. We will come back to this question later. It's because the definition of validity is kind of weak. It's saying that x, y pairs drawn from the distribution should lead to a 90% chance of coverage, but there's no requirement that that chance of coverage should be sort of the same for like this region of X versus that region of X. So what we're seeing is that when you choose the score function, the weak notion of coverage that conformal ensures will hold whether we made a good choice or not. But its usefulness and sort of its stronger properties, at least as we can observe empirically, are extremely sensitive to choosing a good score function. And this is kind of like separating our job as people who pick a good model for the data from conformal prediction's job, which is to offer a guarantee, even though it's weak, but it holds distribution free. So it's separating these two tasks. The analyst's task is to choose a good score function. Conformal prediction's job is to guarantee distribution-free validity, regardless of whether the analyst happened to do a good job or a bad job of choosing that score function. Okay, we will come back at the end of today, if we make it time-wise, to talking about many different examples of score functions that are suited to lots of different problems, but this is just a little preview. Okay, so to summarize so far, what we've seen is that split conformal allows us to start with any model or score as long as it was pre-trained. We fitted it before we looked at the calibration set, and then it has valid predictive coverage. Again, we are still assuming exchangeability. We're not allowing distributions to change over time. We'll come back to that later. But the drawback is that the model/score is only fitted on, say, half of the data. And so, of course, I feel like I need data splitting, because otherwise, how do I get a holdout set to know how wide to make my margin of error? But at the same time, I don't want to reduce my sample size and make the model less accurate. So what we'll look at now is what strategies we could use that avoid data splitting. And that sounds kind of impossible. If I'm not making assumptions, it seems like I need a holdout set in order to let the data tell me how good my model is. We'll see now that there are alternative strategies as well. Okay, so with that, let's go to full conformal prediction. So the intuition is that while split conformal splits the data into two parts, one part has the job of fitting mu hat, or more generally, the score function, and the other part is for kind of calibrating how good or bad your model is. Full conformal is going to use the entire data set for both jobs. And this sounds impossible. Like, how do you know what to do without a holdout set? So let's see how it works. We'll see that we actually do need an additional assumption that was not necessary for split conformal. The assumption is that when I train an algorithm, so for example, when I run a regression to produce mu hat, or for the second type of score function, when I take my training data and I run a regression to produce both mu hat, my estimated mean, and sigma hat, my estimated local scale. All of those things need to treat the training data symmetrically, which is a very natural property if you're like not in some kind of time series setting. If you believe you have IID data, then it's very natural to assume that shuffling your training data set should not affect the outcome. One thing I want to mention, because this is a question that often comes up here, is what if we're doing something like stochastic gradient descent, where the data is not treated symmetrically because I first descend on one data point and then on another and so on. It is sufficient for this assumption to hold in sort of a random distributional sense if your algorithm is randomized, like shuffle the data and then run stochastic gradient descent. That's fine too, but I'm just not writing the details on the slide. Okay, so in order to understand how we can effectively get the same benefit as holdout data of telling us how good our model is without actually having holdout data, let's start with not the procedure that you can run in practice, but let's start with a thought experiment. What if, for the problem of predicting the test point, I actually somehow could access the test point? So again, this is impossible, but it's a useful thought experiment. So let's say that when I run my regression, I actually fit the model to both the training data and the test point. So I run, least squares or whatever, and we'll notice that we're including the test point into my call to the algorithm. Again, this is impossible in practice because that's exactly the quantity that I'm trying to predict. But imagine we could do this. If we could do this, and then we compute all of the residuals on the training and test data, and then we ask, is it the case that the test residual is in the bottom corrected 90th percentile of the training residuals? If we could do this, then exchangeability plus symmetry of the algorithm ensures that the n+1 residuals are all exchangeable with each other. And just like for split conformal before, what that gives us is that this inequality has at least 90% probability. If you have an exchangeable list, you have a 90% chance that any one entry is in the bottom 90% of that list. Okay, before we keep going, let me compare and contrast to holdout methods. In holdout methods, the question that's being answered is, since training residuals are overfitted but test residuals are not, let me get a holdout set. On the holdout set, residuals are not overfitted, and so they're more representative of test points where, again, residuals are not overfitted. In this case, it's kind of the reverse. It's saying, I'm going to overfit to my training data, but let me actually also overfit to my test point. And then everything is exchangeable again. Okay, now of course this is impossible. So instead, the way that we do this is that we plug in a guess for the value of y, and then we run this procedure as though that were the right value of y, and then we repeat. So here's the idea. So this is the exact same thing as the last slide, except instead of the actual value of y, I'm plugging in little y, which is a guess. It's a hypothesized value for the test point. Now for every value little y, and we might already ask, hang on, that could be infinitely many. We'll come back to that in a second. For every value little y, I'm going to run this procedure and check if that inequality holds or fails. And then what we're going to do is take all values y for which it holds and include those in the prediction interval. And if it fails, then I don't include that value y in the prediction interval. Okay, I want to point out that split conformal can actually be viewed as a special case of full conformal. Let's say you pre-train a model, and then now you give me a training set, and my algorithm is this. No matter what data I observe, the output of my algorithm is the pre-trained model that you gave me yesterday. In that sense, that's a special case of full conformal. But in general, full conformal uses algorithms that do depend on the data. And as a result, this is computationally very expensive or even impossible because I have to refit my neural net or whatever to every single value y in the real line. So we'll come back to that computational issue in a second. But theoretically, this is how this works. Is there a question in the back?
So for this reduction from full conformal to split conformal, we need to select the holdout set at random, the subset of holdout. We need to randomly divide the training test, or just?
Yeah, so when I say it's a special case, we're actually re-indexing the data. Split conformal is a special case of full conformal if I were to run full conformal only on the n1 many calibration points. So you first split the data. In practice, you'd shuffle your data. But in theory, IID data does not need to be shuffled. You could take the first half and the second half, and then running full conformal on the second half, that's what split conformal is a special case of.
Can I
Yeah. Uh-huh.
Suppose we're fitting these modern models that have zero training error.
Yes.
So all of these are trivially true?
That's right. So then your interval would just be infinite.
Correct.
What that means is that we've chosen the wrong score function. So again, this is for a specific score function. We could do something different that avoids overfitting by doing leave one out or whatever. So that's just the question of choosing the score function appropriately. Okay. So full conformal has the exact same theoretical guarantee as split conformal. So first, basically, the steps of the proof are the same. We need to check that coverage is equivalent to this quantile event, and we need to verify exchangeability of the scores or residuals. In the interest of time, I'm going to skip over those because it has a very similar flavor to the proof for split conformal. Basically, the idea for full conformal is that even though I'm running the procedure for every value little y, the only thing that matters for coverage is, did I include or exclude the actual value of y? So you can think of the whole real line. I'm rerunning my algorithm every single time. Here's the actual value of y. The only thing that matters is when I get to this point, did my inequality that determines inclusion or exclusion succeed or fail? Okay. Visually, I just want to point out that full conformal means sweeping over all possible values of y and changing your fitted model for each value of y. Okay, so now coming back to the question of the score function, just like for split conformal, full conformal can be any score. It doesn't have to just be the residual because that's very limiting. Generically, what we mean by full conformal with an arbitrary score is that the definition of an algorithm is any map that takes a data set and returns a score function. With that in place, the definition goes through immediately with just that generalization. Okay, here's an example of what this looks like in a categorical data set where it actually is possible to enumerate all values of y. Here's the wine quality data set. The features are just like different features of the wine, and the thing I'm trying to predict is a rating between 1 and 10. So what I need to do is I need to rerun my regression for each possible rating. So I sweep over all possible values of y. And then I also want to point out that you need to redo this also for each test point. And finally, you end up with prediction intervals, and the true value of y should get covered 90% of the time. Now, if I have a real valued response, in principle, running full conformal requires refitting the model for every single value of y. That's impossible. I'm not going to go into details, but in general, what you actually do is you sweep over a grid of y values. There's some versions of full conformal that make that theoretically rigorous. And then there's also special cases of simple algorithms like my score function is the residual for ridge, where you can get closed form solutions to this. Okay. A number of questions have been asked about like the distribution of the data changing and so on, and I just want to mention that in part 2 we will cover some of these extensions, but for today everything that we're talking about is, first of all, only giving coverage in this weak sense. You might undercover for certain values of x and overcover for other values of x, and also we are not yet allowing for distribution drift. We're still assuming IID data. Okay. So far we've looked at split conformal and full conformal. And they're on sort of two different extremes of like statistical versus computational efficiency. Split conformal is very easy to run, but you have sacrificed sample size and you have a less accurate fitted model or more generally score function. Full conformal is computationally infinitely expensive to run, at least for a real valued y, but it doesn't throw away any data from the training process. So we might want to look for options in between, and so we could ask whether cross-validation is going to let us do that. Okay, so what if we do leave one out cross-validation, which in this field is sometimes called jackknife? So I'm going to center my interval at a model that's fitted on all the data, so I haven't thrown anything out from the training process. But then I'm going to rerun my model like n times for leave one out and get the leave one out residuals to tell me how wide to make that margin of error. So that is a data-driven method for quantifying my uncertainty and my prediction. And of course, we would expect that this is going to work great in practice, and it often does. I'll come back to that question of whether it's distribution-free valid in a second. I just want to mention this is the leave one out version. Of course, in practice, for large data sets, it's more common to run, say, like 10-fold cross-validation, where the procedure looks exactly the same, but we refit the model only 10 times instead of n times. Okay, So here's what this looks like in practice. It typically works very well. The thin black lines are the leave one out models that are fitted. And you can see that they offer some variability to help us know that there's some uncertainty in our predictions. And typically in practice, you would generally see the right coverage level. But the problem is that there is no assumption-free theory. You actually do need some assumptions in order for coverage guarantees to hold. And so here's an example, which is that if I'm doing least squares that's getting close to the interpolation regime, so n and d are similar, we actually get under coverage and more variability in my coverage. So the purple curve is when I have like a high n, and the green curve that has a lower mean of coverage, 85% instead of 90%, is when the problem is more ill-conditioned. So the theory really only holds under some regularity conditions / asymptotics. Even though in practice we do often see the right coverage levels, if we have instability, meaning the models are super sensitive to perturbation, like with ill conditioning, you can get under coverage. So theoretically, where does this come from? It comes from the fact, to compare this to split conformal, that in split conformal, I'm calibrating the width of my interval using the holdout residuals, which are exchangeable with the test residuals. That's because they're all the residuals of fresh data on the same pre-trained model. But for cross-validation / jackknife, the residuals that I'm using for telling me how wide to make the margin of error are the leave one out residuals, which have a different distribution than the residual of the test point, since that's not on a leave one out model. And so you don't actually have exchangeability. Now, of course, we expect in practice these behave similarly, but that is making some assumptions. Yeah?
So your SI seen in the split setting, you need some assumptions on it, right?
For what? Sorry?
The SIs in the split setting.
You actually don't need anything. No, and it's because quantiles are working in quantile space. Like, for example, saying that the sample median will with high probability lie between the population 45th and 55th percentile. Those types of statements are independent of the distribution of the data, because I'm only working in quantile space. Basically, if it holds for uniforms, it holds for everything, because it's only a statement about ranks, and ranks are completely distribution free. So that's why there's the finite sample correction. So instead of taking the 90th percentile, I take the 1 minus alpha times 1 plus 1 over sample size.
So even if SI has a massive variance of
absolutely doesn't matter. These are completely distribution-free statements. Yeah. Okay. Okay. So sorry, let me just double check. You want me to end at 5 minutes before? All right. So if we look at jackknife, we can define it like this, where the jackknife interval is between the 10th and 90th percentile of my prediction plus / minus my residuals. The reason for this change is that quantiles are defined in a non-symmetric way. If you have the list 1, 2, 3, 4, the definition of quantile that we're using would put the median at 2, not at 3. There's this little asymmetry. This technical point is absolutely, you can just absolutely ignore it. Basically, the jackknife is looking at the quantiles of predictions plus or minus residuals. So in order to get distribution-free coverage, we propose this different method called the jackknife plus, where basically the prediction interval uses predictions that come from the leave one out models rather than the fully fitted model. So in a picture, here's what this looks like. If I run leave one out cross-validation, a visual way to construct the interval is to look at the prediction for the test point plus or minus all the leave one out residuals. For jackknife plus, we start with the leave one out predictions for the test point, so that's why these centers move around. Again, plus or minus the leave one out residuals. Empirically, what we can see is that jackknife can lose coverage in a really unstable regime. This is linear regression with n approximately equal to d, whereas jackknife plus does not. And what the theory tells us is that for jackknife plus, at most, in a distribution-free, zero assumption setting, you can only ever double your failure of coverage, so 80% instead of 90%. In practice, you actually just see 90%. Whereas for jackknife, the coverage can drop down to 0, like we're almost seeing that in this plot. You can also do the cross-validation with k-folds rather than the expensive leave one out. You can do the distribution-free version of it. We call that CV+. Again, I have like 1 minute left, so I'll skip the formalities. What I do want to point out, sorry, I just lost what was happening. There we go, is that this is related to older work by Wolf et al. Called the cross-conformal method, which is basically a distribution-free cross-validation type approach for using any score function rather than necessarily like a regression model plus or minus residuals. So here's the theoretical guarantee for cross-conformal / CV+ and jackknife plus. You can do distribution-free prediction. Again, absolutely no assumptions. The residuals can behave however they behave. And at most, you lose a factor of 2 in your error. Again, in practice, you would more likely see 90%, but in the worst case, you could see something like 80%. OK. Oops, sorry. So since we are out of time, let me just take 1 second to summarize what we've seen for the cross-validation style approaches to conformal. What I am not covering at the end of these slides, but I'll cover at the beginning of next time, is different score functions you can choose and how that helps conformal perform as well as any model-based method. If you have a good model, conformal will not make you lose the accuracy and informativeness of your performance. But just to summarize what we've seen so far, at one end we have split conformal, which loses some statistical accuracy due to data splitting, but is very efficient to implement. At the other end, you have full conformal, computationally very expensive, but very efficient for how it uses the data, and really beautiful mathematically that it lets us do something that seems impossible, having inference without holdout data. In between, you have these cross-validation style approaches whose theory is still distribution-free, but a little bit weaker because it has this factor of 2 that the two extremes do not have. But what it lets us do is basically trade off between computational and statistical efficiency. What all of these methods have in common is that they are completely flexible. You can bring any model you already have, so whatever state-of-the-art model you want to use. It doesn't matter if there's no closed form expression for it and no theory for it. Put conformal / these cross-validation methods on top, and we have distribution-free predictive inference guarantees. OK, so I'll stop there and we'll pick up tomorrow. Very happy to chat more and take questions.